So let's start off looking at the parts of the sextant. The foundation of the instrument is its frame. The frame can be made of metal or plastic and just acts to hold everything together. It's important for the frame to be solid as it allows the instrument to be as precise as possible. Generally, a metal sextant will maintain accuracy better than a plastic one, and that's just down to the rigidity of the frame. But the big advantage of a plastic one is that it's cheaper. It's the shape of the frame that gives the sextant its name. It covers about 1/6 of a circle or 60 degrees, with the Latin being sextans. At the bottom of the frame you've got the scale. Notice how the scale runs from 0 to 120 degrees, even though the sextant itself only covers 60 degrees. This is because of the double reflection principle, which the sextant employs to take its measurements, and we're going to come on to that shortly. Attached to the frame is the index arm, and the index arm is the main moving part of the sextant, and you use it to actually take your measurements. At the lower end of the arm, you can see that it lines up with the scale, so you can read off your actual measurement. At the bottom of the index arm is a vernier scale and a micrometer drum. These are used, along with the main scale, to get a very precise measurement. The sextant should be able to measure angles to within 0.1 minutes with the vernier scale. Next to the vernier scale is a clamp, and the clamp is used to release that scale so that the index arm can move freely. And you'll need to release the scale using the clamp when you're wanting to take a sight, but we're going to cover that in the third video when we're looking at taking sights. The mirror that's attached to the index arm is the index mirror. It's attached rigidly to the arm so that it moves as the arm rotates, and the scale that we looked at is related to the angle that you use the index arm and consequently this index mirror. The second mirror is the horizon mirror, and it's attached rigidly to the frame. You can see that this mirror is part mirror and part see-through. This is because you need to be able to see both the horizon straight ahead and the reflection of the celestial body that you're trying to measure. And this will become clear again in video 3 when we're actually taking measurements. Some sextants will have a semi-silvered mirror instead, and this makes this sextant a little easier to use, but it increases the cost. Opposite the horizon mirror you have the telescope. The telescope lines up with the horizon mirror so that you can see down the sights and see straight through it. Notice the angle that the horizon mirror is mounted at. It means that when you're looking down the telescope, the reflection in the horizon mirror is the index mirror. Finally, in front of each mirror you've got a set of shades, and you need to use these when taking sights, particularly sights of the sun, so that you can protect your eyes. If you don't use the shade, you can actually burn your eyes, and this is why so many old sailors would wear an eye patch. So we've assembled the sextant, but how does it actually work? This is where the sextant principle comes in. When the sextant is set at 0, looking straight at the horizon, you can see that both mirrors are looking at the exact same spot. The image in both parts of the horizon mirror should be identical. When you start to rotate the index arm, the image in the reflected part of the horizon mirror changes. The angle along the scale corresponds with the angle between the objects that you're looking at. You see how the scale will measure all the way to 120, not just the 60 degrees that the frame covers. And this is the sextant's unique selling point, its operational principle. The sextant works on the scientific principle of double reflection. With basic reflection, the angle of incidence, I, equals the angle of reflection, R. The angle of incidence is the angle between the normal, which is the line perpendicular to the plane of the mirror, and the incoming ray of light. The angle of reflection is the same but for the reflected ray. When you introduce a second mirror parallel to the first, you can see the ray of light continues with all the same angles I and R. Due to the law of reflection, we know that I and R are both equal, so we can actually just call them I to keep things simple. But as soon as that second mirror is no longer parallel to the first, an interesting effect occurs. Let's rotate our second mirror now by an angle, which we're going to call X. The ray of light still interacts with the original mirror in the same way. But now when it hits the second mirror, the angle of incidence has changed. It's now I plus X. And then due to the law of reflection, the angle of incidence equaling the angle of reflection, the angle of reflection here equals I plus X as well. If we look solely at the second mirror, the total deflection of the ray of light is I plus X plus I plus x, and rearranging this gives I plus 2x. Compared to the first mirror, the difference is 2x. Overall, the reflected ray has been deflected by twice as much as the angle between the mirrors. This is the sextant principle. When a ray of light is reflected by two mirrors in succession, the angle between the incoming and outgoing ray of light is twice the angle between the mirrors. Now that we understand the principle, we can head back to the sextant and see it properly in action. We've already said that when set at 0 degrees, both rays of light come from the same direction. If we change the angle between the mirrors, say we rotate the index arm by 20 degrees, the rays of light now come from different directions. Although the angle between the mirrors is only 20 degrees, the angle between the rays of light is 40 degrees. This is that double reflection principle in action. The scale at the bottom has been calibrated to give the angle between the rays of light, not the direct angle of rotation of the index arm. This is why the scale reads all the way to 120 degrees across just 60 degrees of index arm rotation. Just look at that angle that the sextant can measure at its extreme setting. This is the sextant's huge advantage over the instruments that came before it. So, now we understand all the principles. In the next video we can look at the sources of error and how to correct them, before we move on to taking an accurate reading.